I'm Gongde from UC Riverside. I'm very happy to come here to present my research. I also want to thank to organize such a good seminar to give me an opportunity. So today I want to talk about my research on photocatalytic removal of hexavalent chromium by highly reductive titanium dioxide nanocrystals. First, I will give you some background information on chromium and about the toxicity and regulations and the occurrence and the treatment technologies and challenges. And then I will propose my research objectives and the approach I used in my project. Then, after that, I will focus on my research findings in the following three aspects. Then I come to my conclusion. So for chromium, actually there are multiple oxidation states, but there are only two stable forms in natural environment. The first one is chromium-6, hexavalent chromium. It is highly toxic and carcinogenic, and also it has the higher mobility in both water and soil. But for chromium-3, actually it is essential element at trace level, and it can be easily immobilized as chromium hydroxide solids in neutral pH ranges. So based on this, we can see one strategy for chromium-6 remediation is to transform chromium-6 to chromium-3. And there are some regulations for chromium. For federal maximum contaminant level, US EPA has regulated total chromium level in drinking water at 100 microgram per liter, but there is no regulation for chromium-6. For California, we have more strict level for total chromium at 50 microgram per liter, and in 2014, there is the new regulation for chromium-6 that is 10 microgram per liter. So it's kind of a big challenge for public water utilities to meet this level. Sources of chromium-6, there are two main sources. One is anthropogenic activities, so like the industrial production of dye, pigments, or electroplating process that can produce large quantity of wastewater containing chromium-6. The other one is natural occurring. We know some minerals containing chromium. So under certain conditions, like in the presence of oxidant manganese dioxide and at alkaline pH range, chromium-6 can potentially leach out from the minerals and contaminate the groundwater. So this figure shows the kind of statistical distribution of chromium-6 level in treated drinking water across the US. The analysis has been done on the basis of the total number of public water systems, and we can see the whole nation are divided into 10 regions, and we can see in most of the regions the chromium level is in treated drinking water less than 1 microgram per liter. But in region 6 and 9, they have the highest percentage of chromium-6 level greater than 10 microgram per liter. So there are some sampling analysis for region 6 and region 9. They found these regions with water system having a chromium-6 level greater than 10 microgram per liter, they more dependent on groundwater as drinking water sources. So that indicates the natural occurring of chromium-6 is kind of a big source for chromium-6 contamination in our drinking waters. And in California, the California Department of Public Health also made a survey before on the public drinking water wells. And the survey is for a total 5,477 wells. And among them, 3,342 wells have detectable chromium-6 in water, and around 80% of the total wells have chromium-6 level greater than 10 microgram per liter. And we also have some traditional treatment technologies for chromium-6. The first one is iron-2 based reduction and coagulation. So we use iron 2 salt as the reducing reagent to reduce chromium 6 to chromium 3. But there are some disadvantages for this process. So the first disadvantage is the high consumption of the chemicals, means the reducing agents. We need to add a lot of reducing agents to do the reduction. And also it will produce a large amount of waste sludge. The second one is electrochemical reduction and coagulation. So this is a very kind of promising method for chromium 6 removal. And because it used electrons, kind of clean reducing agent to do the reduction. But it requires high energy input, and also the process capability is limited by electrode surface area. And the third one, and is the most commonly used one, is the ion exchange. So the chromium 6 can be captured by the resin, but the problem is after the resin is exhausted, the regeneration process can produce concentrated chromium 6 waste. So that need further disposal. The last one is biological treatment. So we know some microbes can uptake chromium 6, but the microbes is sensitive to the temperature, to the solution pH, and also this process kind of suffers from the slow kinetics. And also if you want microbes to do the work, you need to give food. So in most cases, we need to add excess organics for microbes to do the reduction work. And recently, photocatalysis actually has attracted much attention, and P25 titanium dioxide has been widely used as a photocatalyst. And typically, when we shine UV light on the nanoparticle, the electrons on the valence band will transfer to the conduction band. Cb is conduction band. Leave holes, H+ holes on the valence band. The electrons kind of active. It can further transfer to the surface to reduce chromium 6 on the top corner, to reduce chromium 6 to chromium 3 hydroxide. But also, electron can go back to valence band to recombine with the holes on the valence band to generate heat. Actually, the recombination process is kind of much faster than electron transfer to chromium 6. So we see chromium 6 removal efficiency is very low for the traditional photocatalyst. So to address this issue, people usually add external organics like formic acid and methanol to capture the holes on the valence band. So in this way, only electrons are left on the nanoparticle, so it can release for the reduction. But one drawback for that is if you add external organics, it can deteriorate the water quality. So in my project, we try to synthesize reductive titanium dioxide nanocrystals with intrinsic hole scavenging effect. Hole scavenging effect means we use something to kill the holes, only left electrons on the catalyst for the reduction. The idea is we cap sacrificial ligands on the surface of titanium dioxide. Then once holes generated, it will be trapped by these ligands. So the electron have prolonged lifetime to travel onto the surface for chromium 6 reduction. So we select the diethylene glycol as the sacrificial ligand. We do thermal hydrolysis of titanium tetrachloride at 220 degrees C for 3 hours. Finally, we get our product. Then after we get the catalyst, we want to test the performance. In my project, I used battery reactor system. So at the light source, the UV light source is a medium pressure UV lamp in the middle, and the battery reactor are coarse tubes. So during the experiment, the kind of the reactor is rotating around the UV lamp. So after a certain time or interval, we take samples and monitor the chromium-6 concentration. So this is the result. So on the left-hand side, the TEM image shows the morphology of nanoparticle. I know it's not very clear, but it's very small. It's only 5 to 10 nanometer, very small. And we do XRD to get the composition of catalyst. All different diffraction peaks can be indexed to anarchist titanium dioxide. So these two results demonstrate that we get titanium dioxide, and it's a small nanoparticle. And the FTIR spectrum on the right shows our catalyst has the characteristic peaks from diethylene glycol. So that indicates we successfully kept this organic molecular on the surface as the sacrificial ligands. Then we want to evaluate the performance for chromium-6 reduction. Here I choose two 100 microgram per liter and 20 milligram per liter to simulate chromium-6 level in both drinking water and wastewater. So we can see in both cases our catalyst, the black curve, has much better performance than standard P25 titanium dioxide. Then we also look at the impact of catalyst dosage for the reduction performance. As we can see, when we increase the catalyst dosage, the reduction efficiency is highly increased. For example, for 20 milligram per liter of chromium-6, at 50 milligram per liter of catalyst, we need 120 minutes to remove almost all chromium-6. However, if you increase the dosage from 50 to 500, only 10 minutes is required. We also look at the impact of solution pH on the reduction efficiency. For drinking water, the pH is around neutral, but for some wastewater, it's kind of base acidic pH. So we tested the catalyst performance in both cases. We found our catalyst actually work for both neutral and acidic pH, but it has much better performance at acidic pH. We can see a great difference, especially for chromium-6 at 100 microgram per liter. There is the obvious lag phase for the black curve at neutral pH. That is because at neutral pH, the reduction product is chromium hydroxide solid. So it can deposit on the catalyst surface, block the active sites, which led to a lag phase in the black curve. Then another issue we want to address for the catalyst is, since we have a very small nanoparticle, it's only 5 to 10 nanometers, very small. So it's going to be very difficult to separate from the suspended system. So we try to introduce the magnetic properties to the catalyst. In this way, we can use we can apply external magnetic field to separate the catalyst out of the system. So here we synthesized nanocomposite. We add two more things to the catalyst. One is iron oxide, that is the magnetic material. So that is the core. Then we protect the magnetic material is silica dioxide. Then we put titanium dioxide on the surface. So the figure here shows when we apply magnetite, the catalyst can be easily separated from water. And also we tested the performance of this magnetic catalyst for chromium-6 reduction. For 1 milligram per liter of chromium-6, we can see to achieve around 90% removal, it requires around 60 minutes. Actually, the performance is good. Then I come to my conclusion. First, we prepare a reductive titanium dioxide nanocrystal, and we found that our catalyst can achieve a fast chromium-6 removal. And also, if you want to increase the performance, you can increase the catalyst dosage. The last one is we can modify the catalyst with the magnetic properties. In this way, the catalyst can be easily separated from the water. With here, I want to wrap up my presentation. I'd like to thank my advisor, Dr. Haizhou Liu, and my collaborator from Department of Chemistry of UC Riverside. And also, I want to thank my funding sources from Catalysis Center of UC Riverside and also Los Angeles Center for Urban Natural Resources Sustainability. Thanks.
Hi, I'm Colleen Fisher, and I'm from Poly Pomona. I'm a Master's of Regenerative Studies. And I am going to give you guys an update on my thesis project. It's not done yet, it's in the middle, so I only have a few results, but this is the beginning of it. It's called The Interception of Particulate Matter by Street Tree Leaves in an Inland Valley of Southern California. Just outlining my presentation, I'm just going to give a little background information and then go over my purpose, my 4 hypotheses, and then some of my methodology, results, and some of my current conclusions. First off, last year I read an article in the Los Angeles Times that said people living near the 60 freeway in Ontario are breathing the dirtiest air in Southern California. Excuse me. I didn't plan that. So I was wondering why that was, and a lot of it is because of diesel trucks. So I looked into it more, and diesel trucks produce PM 2.5 and PM 10, which are the cause of a lot of premature deaths, especially in Southern California, which are linked to cardiovascular disease, asthma, lung cancer, all those great things. So I wanted to look at how trees can help filter all these particulates out of our air. So I based a lot of my research off a study by Sabo et al., which was in 2012. And they found that leaves of street trees that are slightly waxier or have hair on them are better at capturing particulate matter. I also wanted to define say what I'm defining my particulate matter sizes as. I'm going off the study by Sabo et al., and PM10 is defined as any particulates that are 10 micrometers in diameter and bigger. And then PM 2.5 is between 2.5 and 10 in diameter. The purpose of my study is to determine which street trees are most efficient at capturing these particulate matters. And it's not going to look at the composition of the particulates, just the accumulation and the size. So hopefully this research can help city planners decide what are the most effective street trees to plant to improve air quality. So I have 4 hypotheses. My first one is I believe that trees with leaves with more abundant trichomes and or complex vein structures will be more efficient at particulate capture. Second, out of my 5 species, which I'll tell you in a second, I believe that Plantanus racemosa will be most effective because it has hairy tufted vein axils on its underside, and it's the most out of my species. And then I'm also looking at stomatal conductance. So I believe that leaves with higher stomatal conductance will be better at filtering these particulates, just because they have an increased ability to uptake particulates. And then lastly, I'm comparing all seasons. So I believe particulate accumulation will be highest in the summer, just because there's more pollution and there's less rain. So I am studying in Claremont, that area, and I'm focusing on 3 different streets in Claremont. So I'm looking at Foothill Boulevard, Indian Hill, and Arrow Highway, and I'm comparing truck routes versus non-truck routes. So Arrow and Foothill are truck routes and Indian Hill is not. One reason I chose Claremont is they have a very handy GIS map open to the public. They named the Urban Arboretum, and it has listed every street tree in Claremont, which is pretty amazing. So you can just click on one of the dots. The ones that are light green with dark green around, those are native species. So I got a really good source to find what trees they planted and where they are. So that's how I sort of determine what trees to use. I chose 5 different species, and I chose 3 evergreen and 2 deciduous, as well as a mix of native and non-native. So my evergreen species, I chose Quercus agrifolia, and this is found on all 3 of my streets, so it can be used as a control. I chose Quercus ilex, it's found on Arrow Highway, and then Eucalyptus sideroxylon, which is found on Foothill. And then for my deciduous, I chose Plantanus racemosa, found on Indian Hill, as well as liquid amber styrosiphylla on Arrow Highway. So when I'm going out and collecting leaves from my trees, I'm looking for trees with an average diameter breast height of 45 to 60 centimeters. I'm also looking for leaves on the side that's closest to the road, because that's where the pollution is closest to. And then leaves from the lower canopy, because they have the most direct contact with particulates, and also it's easier for me to sample rather than going up and climbing the trees, which I have had to do. And then I'm choosing 6 individuals from each species, so 6 trees from each of those 5 species, and then taking 4 leaves off each of those individuals. But then for Quercus agrifolia, as I said, I have 6 individuals on each of those streets, because it's going to be my control, so that's 18 total Quercus agrifolia. I'm also taking stomatoconductants. So I take those on the leaves before I take the leaves off, and then I bag the leaves and bring them to the lab for filtration. And then I spend a lot of time in the lab. I have 2 different types of microfilters, one for PM10, one for 2.5. And first I wash my leaves with water to get all the particulates off the surface of the leaves, and then I use acetone after that to get them off the waxy layers. So I'm also comparing surface and epicuticular wax layers of particulates. I'm also clearly interested in the leaf characteristics. So I'm using a Lycor leaf area meter, and then also weighing the leaves once they're dry to look at mass and size. And then I'm using binocular dissecting microscopes to look at the trichome presence, epicuticular waxes, and venation of the leaves. And then lastly, I'm using a micrograph using digital cameras just to see the particulates on the surface and what it looks like. So I have 2 graphs to show you today. Again, I still have a lot of information to process. Mostly I've just done data collection. But this is my graph of particulate matter 10 using H2O to wash them. So this is on the surface. Some things to highlight here are that out of all the species, Quercus ilex has been the only one that has actually increased the particulate accumulation from summer to fall. Every other species has decreased. The highest particulate buildup in the summer are Quercus agrifolia, found on Arrow Highway, Quercus ilex, and Quercus agrifolia on Foothill. And just to note, Arrow and Foothill were my truck routes, so that's nice to see. Highest in the fall were Quercus ilex, again Quercus agrifolia on Arrow, and then Quercus agrifolia on Indian Hill. In both seasons, liquid amber styrosiphylla was lowest, which is good, because it's non-native and not great. And then my other graph is just showing PM 2.5 using H2O, so this is the surface level particulate buildup, and the results are very similar. Again, Quercus ilex, still the only one that actually increased from summer to fall, and then the highest in both the summer and fall are Quercus agrifolia on Indian Hill, Quercus ilex, and Quercus agrifolia on Foothill. And again, liquid amber styrosiphylla is lowest. Just concluding those results, from what I have thus far, it looks like my oaks, Quercus agrifolia and ilex, could be the best choices for city planners to plant. Specifically, agrifolia would be great to see. It's a native species, and if it does the best at particulate capture, that would be great. My hypothesis of Plantanus racemosa isn't really coming in clear yet. It's one of the lower ones in particulate buildup, so we'll see how that goes. And then again, liquid amber styrosiphylla is the least efficient. But I still need to do data collection and a lot more graphs and processing. So that's what I have thus far. And then my next slide is just questions, but we'll save those for the end when you can grill us all together. So, thank you.
Hello, everybody. I want to thank you all for having me. My name is Peter Ibsen. I am a PhD student at UC Riverside, and most of my work focuses on, like the previous one, urban trees across Southern California, but specifically I'm looking at them across the climate gradient that we find down here. So Southern California has a really interesting dynamic climate gradient and one that is also in the process of changing. From beach to desert, we can see an increase of, I believe it was around 26 degrees in average August temperatures, and across the board that's going to be increasing. This is coming out of UCLA, one of their climate labs is recently published, where they scaled down multiple global climate models just to Southern California. So we're seeing that there's going to be an increase across this huge gradient. This makes it a very interesting place to study the future effects of climate on urban trees, especially in multiple species found across Southern California. And even more interesting, I feel, for my research than just a dramatic increase in average temperatures is that there's an estimated increase in days of extreme heat. And I see there's some formatting issues where I try to move that 35 over the 95 because Fahrenheit is non-scientific. But basically that we're going to be seeing increases in days of extreme heat across the board in many cities in all the cities in Southern California. And really where you're going to see the biggest magnitude of those changes is in our coastal cities, in Irvine and Long Beach and Los Angeles. By mid-century in the business as usual models, there is a predicted almost fourfold increase across the board. And by end of century, we're looking at order of magnitude increase for some of these cities. Also interestingly with this is that you can see the extent of increase isn't as big in Palm Springs and the desert cities, but you can see that Palm Springs projected today is very similar to what Riverside, where I live, which is already very hot, is projected to be by end of century. And Riverside today is very similar to what is projected for Los Angeles end of century. So this brings me to my questions of what I'm looking at is how urban trees that are planted across this gradient, where we have many of the same species planted from beach to desert, whether this trees planted in Palm Springs and Riverside, their effects of climate on them might be able to predict the effects of climate on those same species in Los Angeles. And one of the ways I can look at this is because of the power of irrigation. There's a lot of issues, I'm sure many of you know who work with trees, about drought and how trees are going to respond to drought. And a lot of the concerns with that is in soil. And soil drought is that we have fixes for that. We have irrigation. And while it still is an issue, you can have, this is Palm Springs as seen from San Jacinto, you can have an incredibly arid, dry, low-lying desert, and if you pump enough water into it, you can have strips of golf courses running all the way through. And so that, in some cases, can help mitigate the issues of soil drought. What it cannot mitigate is the issues of atmospheric drought or aridity. So across Southern California, as you saw before, we have increasing climate gradient of temperature, but equally so, aridity and temperature go hand in hand. And this is aridity as measured by the vapor pressure differential, and this is mean maximum summer vapor pressure differential. So we have a dramatic increase in aridity, and that is not being able to be controlled for by irrigation. So even though you might have the same species in Palm Springs and Riverside, they are definitely encountering very different climates. So for my study, I looked at 10 different species of urban trees. These are where I sampled them from. I got about 160 different individuals of those 10 species. 6 of them were being able to be found from the beach to the desert. 3 of them, I believe the Lostema convertus, Quercus agrifolia, and Afrocarpus falcatus were not found in Palm Springs at all, which I find that's a little interesting quirk, as in even in a lot of Palm Springs and Southern California desert planting guides, Quercus agrifolia is listed as a drought-tolerant species, yet is very rarely found planted as horticulturally in the Palm Springs region. And then one of my species I was looking at, the pink dog catalpa, is very rarely found around coastal regions, gets a lot of mildew issues. So I've got a large dynamic spread of different species that I can look at that have obviously different effects on climate, yet we're still seeing a lot of them planted on this gradient. So also interestingly, with these trees, Southern California is dynamic for climate, but it's also dynamic for biodiversity. Here we have a biome map of the world. There's many of these. I like this one because it's very colorful and very, that's a good enough reason for me at the moment. I'm on a time budget. Within these biomes, all these 10 species I mentioned are found in many of them. They're all growing. Most of these are growing within a very short radius around this building. But for example, we have our native species, our Quercus agrifolia, or Platanus racemosa, both native around California. All right, just looking at, I'm going to warn you, there's going to be some issues with my slides because all these trees are a little bit pushed off. Hopefully that won't carry on. But basically, we have our native species, and while they're native, they're also coming from different biomes. Quercus agrifolia tends to be found more on hot, dry hills, but then Platanus racemosa, while native, is more of a riparian tree, and you're going to find that in sort of your canyons around Southern California. But then equally, they'll be planted in parks next to Magnolia grandiflora, a southeastern riparian broadleaf tree, Jacaranda mimosifolia, that's a tropical one from Brazil, or even our crepe myrtles, Lagostroma indica, coming from broadleaf forests of China. So all of these biogeographic provinces are sending their trees here, and they're being planted on this gradient. So that's a very interesting way to look at what might be driving some of these responses to climate. Another way that you can look at the variation of biodiversity here is through a phylogenetic diversity, is that my 10 species I have on here, and I'm going to be doing 10 next summer as well, you can see evolutionarily speaking, they're also incredibly diverse. So we're getting trees from across the world, from many different biomes that have very different evolutionary histories. Yet still, you will find magnolia planted next to Chinese pistache with some crepe lagostromas, Quercus agrifolias, and tipus. These are all very commonly found within the same regions, within the same parks. So what I'm trying to see is all of these have different functional responses to climate, but also that are based off of their evolutionary histories and their geographic histories as well. So teasing apart what sort of factors climate will have on these relationships is really important to figure out. So to do that, I'm looking at a set of different functional traits within these trees. Functional traits are basically any measurable part of an organism that influences the organism's health. That's a really brief definition of it. But basically, what I'm looking at are a lot of leaf functional traits. These are traits at the leaf level with a few larger ones like tree height and then wood density being another trait to look at as well. There's literally hundreds of different traits you can measure. These are chosen because they're very represented in the literature and they're very easy to take. So we're trying to get really large ideas of how these trees are functioning, but we have to take multiple, easier measurements that can give us clues to how they relate. A lot of these traits relate very positively with each other. So you have traits such as specific leaf area. This is a very commonly used functional trait measurement. It's basically the area of the leaf, the photosynthetic area on the top of the leaf, as a ratio of its dry weight. And that's very tightly correlated with leaf nitrogen. And together, these are commonly thought of as economic traits. These are traits that are very closely related to photosynthesis in the plant. Interestingly, they're also related to, you can see related relationships between the stomates, the stomatal length and stomatal density, and leaf thickness, which might not be as closely related to the other traits. So we have also a lot of these unknown relationships between all these different traits. And sometimes you can look at these as different suites. You have your photosynthetic traits that might be more related. You have your water use traits like stomates and wood density that might be more related. And you have your leaf morphology traits, your leaf shape and your leaf thickness that could also be closely related, while they all might have unknown or weak traits or weak correlations to each other. There's a lot of work in the literature that looks at every single one of these, but really depending on different species, depending on different locations, they could all be different drivers that affect these relationships. And in the urban area, some of those drivers that I'm looking at are, like I mentioned, evolutionary history, that biogeography, that climate, that aridity. Also, because I'm looking at atmospheric drought and aridity, all different species generally have different ways of dealing with drought, their hydraulic strategies. So one way to get at this is start to measure those hydraulic strategies and see if those themselves are determining how those functional traits change. And in some cases, when the range of trait values start to constrict, you might start to see tree mortality, and why certain species you can have planted all throughout Southern California, but then they hit a wall of climate and you're not going to find Quercus agrifolia or Afrocarpus or the brush box in the desert. Also, in urban areas, we have to consider local environments. All cities are different, they're run differently, parks are different, the natural soils are different, but also the imported soils can be different, so these might also have a lot of effect as well. So I'm going to show some quick results of this. This is a work in progress. I'm going to be coming back here in June with more in-depth results, but I want to take a look at least the traits that I've measured so far and how they're relating. So when we look at these across, this is all the traits I've measured for all the species across all climate. And what we see here, and the blue boxes are where these relationships are significant, we see a lot of what I've mentioned before, that these suites of relationships are appearing. That you have specific leaf area and leaf nitrogen tightly correlated. All of our leaf shape, leaf morphologies are also tightly correlated. DI stands for dissection index. That's basically how much a leaf is dissected, how compound it is. And shape factor is basically a metric of roundness. And you can see that for a lot of these specific leaf area, it is a metric of economics, but also leaf morphology, tightly related to all of them. You also can see that these suites of more water use traits like stomates have a little bit of connection to both. Sometimes leaf nitrogen, sometimes leaf morphology, but you're seeing these suites start to come out. Interestingly, I found no relationship in wood density whatsoever across climate, across species. It was just a shotgun blast of points that meant nothing to me. But to go on with interesting results, when I start to look at these traits across different climates, you can see the relationships start to break down when we look at specifically on the coast. So these are all the samples collected from all my species as close to the coast as possible. Roughly, I broke down my map as we have in basically increments of 7-degree increases. So coastal climate, roughly think of that as like almost up to the 405. The beach to the 405 is about that. But you can see that we start to see some of these break down. Still specific leaf area, tight economic connections, tight leaf morphology connections, but a lot of the water use, a lot of the stomatal traits start to lose their influence. However, and interestingly, we see a difference between the density and the length of stomates. There seems to be certain drivers of those that appear to be more related to economics and more related to morphology. And when we move into the desert, this is where I think the more interesting results come out. Is that specific leaf area, as I mentioned before, it is a metric of the area of the leaf divided by its dry weight. So that dry weight is going to be closely tied to leaf thickness. The thicker a leaf, the more dry weight it's likely to have. And why you often see specific leaf area will always correlate with leaf thickness. However, leaf thickness is also being a trait of leaf morphology, of the leaf shape, and that's why you always see leaf thickness generally correlated with the shape factor and the dissection indices. But when we get in the desert, the specific leaf area starts to lose its connection to leaf morphology, and you actually start to see the stomatal relationships become tightly correlated to leaf morphology. So what we might be seeing here is these suites of traits, while certain traits might not be directly affected by climate, what we might see is these suites of traits as a whole start to be more coupled and decoupled from each other. And this is one way to look at it. This is a multi-dimensional plot. I'm going to spend a minute or so on this because it's kind of a complicated plot, but what we're looking at here is all these individuals and traits in a multi-dimensional space. So the axes here mean very little. What really matters is the closeness of the points. So each of these points here are the different individuals of species. The more physically close each point is to each other, the more related those individuals are. So naturally, you'll see most points collected together are the ones of the same species. So you see species clustering. I mean, different trees are different, that's obvious. But what also we have on here is these red points are each of the traits. And the closeness of each individual to that represents how much those traits are driving all the values within those individuals. So when we look at these together, we can start to see different clusters appear. One you see, which I find interesting, is that certain trees, certain individuals from trees are more related to each other, while we have certain species, for example, like the Fraxinus udii here, or chamois, is not really tightly connected to each other. This might reflect that it has a lot of just variation within its own species, while other trees, such as the Tipuana tipu, might have very less variation based on how it's all clustered together. But in relation to the traits, for example, this cluster here is very closely related to the dissection indices, that being the compound leaves. And what do we see in that cluster? We see the tipu, we see the jacaranda, and we see the chamois, all of our compound leaves. That's not very surprising. But what is surprising is that when we look at these other two clusters, is that we see that concept of leaf shape start to not be the driving influence, but we see really stomatal traits be that driving influence. As we have, for example, in here are pink dawn catalpa, and above that, in this different cluster, we've got the Lostema convertus. Both trees that have at least on the surface, similar looking leaves. They're both sort of wide lanceolate leaves, but they're very dissimilar from each other in terms of their trait values. And those trait values are mostly clustered in one side on stomatal length and the other on stomatal density. So what we're seeing here is, again, those suites of traits start to become, we start to see that coupling breaking apart. We have leaf morphology and then these stomatal traits that seem to be driving a lot of these values and a lot of the variation. Also interestingly, here we have leaf nitrogen and specific leaf area, those economic traits very tightly correlated to each other, but very few values and very few individuals are tied to that. And this might go, and there's a lot of literature that these economic traits might be more driven by, say, evolutionary history rather than climate, so there's going to be less variation in them and less driving forces when you expose to climate. So my next steps in working with this data, and like I said, I'll be back here in June to give you a more full version of this, is start to separate that variation from the species level and the intraspecific level. So this is some of our results coming out across all species, and one, you could look at this and say, like, well, obviously, you see a higher increase in specific leaf area in the mean values, but also the range into the desert. Same with leaf nitrogen. You see an opposite for leaf thickness. You see these trends happening. Again, wood density, bupkis. But what could also be happening here is I need to start separating out the community level arrangements as is specific leaf area actually increasing, or are we just not seeing certain species like Quercus agrifolia, which has a very small SLA in the desert, and more of high SLA species in the desert, or are we actually seeing more variation within species to have a higher SLA when exposed to that extreme aridity? So I need to start separating those out. Also, I've been looking at hydraulic strategies a lot more importantly, and one way of doing this is categorizing species on a metric of isohydric and anisohydric species. And this can be thought of as drought tolerance to drought avoidance. For isohydric species, they will rapidly regulate their stomatal conductance in exposure to aridity and water loss, but therefore they avoid the drought. Conductance is cut off, and then they're able to maintain their water potential within the plant. On the other side, you have anisohydric, which maintain their relatively high conductance at low water potential. Therefore, they're able to continue doing photosynthetic assimilation, continue doing photosynthesis, but are at a higher risk of hydraulic failure. And you can get at these by doing a few different physiological measurements, one being combining the amount of how stomatal conductance drops as the water potential in the leaf drops, and then the other one is looking at hydraulic conductance within the stem, how that changes as water potential drops. And you can see the relatively loss of conductance. And from these, you get a few different metrics. One, the common one being the P50, which is 50%, how much water potential has to drop before you lose 50% of conductance. And from this metric, you can get something called the PG12, which is 12% loss of maximum stomatal conductance, which is theorized to be the point at which a plant has basically shut down, it's completely regulated its conductance to avoid drought. I've done a few of these measurements. This is my measurement of PG12, the point of stomatal closure for all these species. And you can see, again, a wide spectrum of values. And I'm going to be combining this with the P50s as I go on. But from this, one of the interesting things, and this is so far semi-anecdotal, but some of you might recognize that the species that have the extreme levels, the Afrocarpus, the Chamelash, the Quercus agrifolia, and the Platanus racemosa. Quercus agrifolia, Afrocarpus, falcatus are almost never found in Palm Springs, as just I've gone out and looked for them. I couldn't really find any of them. And just from my own experience of going in Palm Desert looking at urban street trees, the Chamelash and the Platanus racemosa seem to be doing the worst with aridity. They're really doing poorly. And at the other end, the Lostemon confertus, the loco out there, also couldn't find any examples of that in the desert. So this is starting to let me to look at perhaps that it's not, the extreme strategies, the end points on this strategy list might not be the best for dealing with climate, that you really want to have more of a generalist strategy found in the middle. And I'll be looking to that and tell you all about it in June. And that's it. That's me doing some physiology measurements in the back of my Subaru.
So I'm Grace. I'm going to talk to you guys a little bit about some of my dissertation research at UCLA. or I'm trying to look for the best ways to quantify urban plant drought tolerance and water use. And I focus on Los Angeles. This is a perfect place to give this talk. So everyone in this room probably already knows the answer to this question, but I feel like we can't say it enough times. So why do urban plants matter? And of course, beyond the aesthetic value of the iconic species like the palms we saw on the last slide, they're providing us with all of these services. They are providing all this habitat for a surprising diversity of organisms. They're increasing property values. They're providing places for children to grow and learn, and providing community spaces. Plus, probably most importantly, they're giving us this evaporative cooling, which is both decreasing our reliance on electricity to heat and cool our homes, and mitigating that heat island effect that we see in a lot of other urban systems. This is especially important in Los Angeles because it's a huge city. It's a sprawling metropolitan area with 3.8 million residents. All of you are familiar with it. In that sprawling metropolitan area, there are 6 million trees to be estimated. That seems like a lot of trees, but we're actually 6 points below the national average, which again, probably most of you already know that. The obvious answer to this is what? Plant more trees. Right? Problem in California with plant more trees is that with all of those great services they're providing us, there's a huge cost. And here, that cost is irrigation water. Almost all of the trees here are living off of irrigation water. This is going to be a big problem when these droughts start to increase in frequency and severity, and we have to start limiting the amount of landscape water we're using. So the solution then is what? Plant trees that use less water. Totally simple, right? Not simple in LA. Because we have so many tree species. There are over 140 species that we've found so far of just trees in LA. Those 10 most common of those trees are only accounting for less than 35% of the total tree volume. What that means is that the common trees are not really common and the rare trees aren't really rare. There's kind of everything everywhere. The reason for that is because it's a nice place to live. Everybody loves living here, right? 72 degrees and sunny and beautiful. You can plant anything you want as long as you're willing to water it, which Peter already touched on, right? But what happens when we can't water those things? It's going to be an issue because all of those 140 species are from different places. They're representatives from almost every community, everywhere in the world. And they're all going to react differently to droughts, and they're all going to need different amounts of water. And I can tell you right now, as a physiologist, 140 species is too many to characterize the detailed drought responses to. So what do? I'm trying to get at this with a scaling approach using functional traits, which Peter kind of already described. The idea here is to take something that's very, very easy to measure and small scale that relates really well to something that is hard to measure and long term. So in my case, I'm taking things at the leaf level and trying to relate them to things that happen at the tree level. So we'll call those our functional traits, and things like drought tolerance and water use would be our performance traits. I'll just use those from now on. So the first step in this approach is to identify the best functional traits. The way that we do that is with detailed physiology, where we can get at mechanisms this way and try to fully understand how the tree works and what's going to happen. The second step is obviously to survey those traits and figure out how they work across the ecosystem broadly, meaning as many species as possible, and then survey those performance traits really narrowly to see if we can kind of get them to connect. And the third thing is to bring it all together and test all of these models and figure out what the best way to predict for the whole system based on our subset of species that we have all the information for. This is a tree. Obviously, we've all seen a tree before. I said I was going to focus on things that are really small, and I love leaves, but there's a reason, not just me loving leaves. The reason is that the leaf, if we need review of our physiology lessons here, the leaf is the pinnacle, the point of the whole tree, right? This is the driver for everything that happens in the tree. So the way that the tree works here is that the relatively dry air outside of the leaf is pulling water molecules from the relatively wet inside of the leaf. So that's creating now a tension, a negative tension in the leaf. That's going to pull on the water that's in liquid form in all of the veins, in all of the leaf, all over the plant. You can think of this like a rope, like it's the dry air is pulling like a rope all of the water all the way down to the roots. So also at the roots, obviously the soil is drier than the inside of the plant too, so it's doing the same kind of thing. The problem happens when both of those are pulling so hard that our rope breaks, and then the leaves can't get the water anymore. That's the idea here, right? So the point at which those breaks happen, we call those embolisms. So species can recover from embolisms, but this isn't really well understood, and it's definitely not quantified at the level that we need it to be to kind of make these predictions. We also don't really know how it happens, so there's a lot of work to be done there, and all of those gaps in this understanding is kind of what was leading me to this next question, which is what do we know about leaf death? The answer is surprisingly little. We actually have no cutoff point in any of the literature for when you can call a leaf dead. So if you walk around and see a wilted leaf, it's impossible for you to say this leaf will or will not come back if you water it again. This is in a lot of other physiological literature. It's called lethal dose 50, or LD50 here. This happens a lot in like viruses, viral load, for example. You can get at models that figure out how many viruses it would take to kill 50% of the population. We don't really have a lethal dose for drought, though. And the problem when we're doing this kind of scaling stuff is that all of our hydraulic measurements that Peter was talking about don't include any kind of recovery. By recovery, what I mean is if we dry it down, if I water it again, is it going to come back? How much of its function is it going to lose? What's going to happen? Like any good physiologist, I did the next thing you do, which is you build a jungle in the greenhouse and you irritate all of the Arabidopsis people, and then everybody hates you in the greenhouse, but you get all of this amazing data. So I picked 19 species, I acclimated them all to the greenhouse, and then I hardened them all for 3 to 14 days. We harden them because greenhouse plants, especially from nurseries, tend to be very sensitive. They don't react the same way that things would on the street at all. So I gave them like a mini dose of drought, like a training drought, if you will, to prepare the leaves so that they would be just like they would if we found them on the... And then I came up with a method to try and quantify this kind of recovery trait. So I take my leaves from the greenhouse, I hydrate them overnight in really high relative humidity so that they're perfect, pretty happy leaves. I figure out how much water is in those leaves, and then I systematically dry them down on the fan, very complex stuff. And then I weigh them again, figure out how dry they are, what water is left, and then I put them back in the water, rehydrate them overnight again, weigh them again, and see how much their saturated water content has now fallen. So that's, once I put them in the oven and dry them down, I can extract from there what's leaf and what's water, and I can get basically something that looks like this. So what you're looking at here on the y-axis is basically our recovery parameter, and on the x-axis then is our dehydration. So our percent saturated water content is how much was lost relative to when I weighed it before when it was totally pretty and happy. Yeah? Okay. If you do that, then 19 times, you get something that looks like this. Okay, from these curves now, I can get kind of exactly what I was looking at, which is a new performance trait that I can use now to be my performance trait for drought tolerance for these 19 species. What I'm going to call that from now on is RWC at PLCR. I know that's a lot. What that means is the relative water content at the percent loss of capacity to rehydrate. I know, like, I've been working on a better way to say this, and I haven't come up with one yet. So if anyone thinks of one, come see me after. So we have this for all these species, and you can see that they're all different because all the leaves are different, obviously. The next thing we need to do, though, is figure out what our cutoff point is going to be. And it might not be obvious when you first look at all of these, but if you take a look at this cleome, which is a desert species, you'll see that it kind of plateaus relative to this California bay, which kind of just declines linearly. So the cleome, basically, I can dry it a little bit and it'll come back totally, versus the California bay, where any amount of dehydration is going to cause it to lose some of its potential to recover. So what that's telling me is that things above 90% aren't really that informative for this kind of scale model that I want to be general, if all the leaves are reacting differently above 90%. But if we look below 90%, everything is more or less linear. So we can continue with something below 90%, but then we need to pick a low point, which the 50%, right? Because we're trying to get at our LD50. But there was a big problem with that, which is these three annoying chaparral species that I dried down for weeks on the fan. Weeks. And nothing. They still come back. So if you check out this, this ceanothus, maybe, yeah, and this quercus, this is the agrifloy that we've been heard about so much. Both the quercus and the ceanothus, I'm drying them down to like lower than 10% of their relative water content here, and they're still bouncing back above 50%. So I can't really extract something beyond the range of my data here. And if we look at this scrub oak, it's even worse. So if I get down to 5% relative water content, it's still coming back to 80% of what it was before. So you might think like, wow, those are amazing. And they are. You're not wrong. But if you don't deal with relative water contents, you might not know what that means, 10% relative water content, which is why I put this picture here. Like these leaves fall apart when you touch them. They're that dry. So what that's telling me is that things below 10% are not really biologically relevant. So 50% cannot be my cutoff either. So from here on, I'm going to use 90, and 75%, because these seem like reasonable values. Now we can finally get to what I wanted to get to, which is my leaf death. I want to know what it takes to kill a leaf, right? And I want to know what it takes to kill a leaf even if you water it again. And I want it faster than having to kill plants and then rehydrate them over and over again, because that takes way too long, trust me. Okay, we can do this now through this model because we just got this recovery parameter that we just talked about. This is RWC stomatal closure, which is how dehydrated the plant has to be before it closes the pores on its surface, or stomata, which Peter was also going into. G-min is the rate that water is lost after those stomata close. LMA is basically the mass of the leaf that's not water, and saturated water content is the mass of the leaf that is water when fully hydrated. So with all of that together, we can create this index, which is exactly what we were looking for, as our new performance trait. The best part about this performance trait, aside from it being a simplified, boiled down 1-point drought tolerance parameter, which is kind of like the holy grail to me as an ecophysiologist, is that it correlates with all of our functional traits, and it all comes back together. So I have here leaf thickness, leaf area, and LMA. All of these, as you said, are part of this economics principle, and they're related to photosynthetic rate, nitrogen mass, leaf lifespan, all kinds of traits, and they're really commonly used in ecology and urban forestry and everywhere. So this is really great because they're easy to measure things that I can go out and measure now for many, many things. Psi-min is kind of a field measurement, which is this one, which is telling us how low, how dehydrated the leaves are actually getting in the field. Those are from literature values, which that correlation is telling me that our TLD is going to be able to be applicable to the field because it's still relating to the things that we're seeing in the field that I didn't even measure, which means quite conservative. Quite conservatively, I can say that this will work. Okay, let's see if it does. So I went on and measured all of these functional traits. For 60 species, I measured 17 traits. I went out with the pole pruners shamelessly in Westwood and at the Arboretum and talked to strangers about what I was doing that were worried about their trees. And we saw, unsurprisingly, we saw enormous diversity. So we have leaf density, leaf area, and LMA again. These are histograms where the y-axis is showing you the percentage of species we found in each of the categories of each trait here. So you see that they're pretty normally distributed and that there are probably species that are more or less well suited for our ecosystem. Probably more interestingly is this trait Turgor loss point, which is how dry the leaf has to get before it wilts, basically. This is a really good drought proxy that people are using everywhere, and it's really great because it's really easy to measure. It's not really a functional trait because it's kind of more informative, but you can measure it like one, which is the perk. So I did that for all those species too, and you can see definitely here that we have a spread of species that are good and bad for the system, but most of them are somewhere in the middle, which is kind of where the complexity lies in this. This also helps me to test how valid my approach is using these functional traits to predict these kind of physiological traits. So here we found a strong correlation between the TLP and the leaf density, which isn't that surprising, but it's strong enough to make predictions. It's really strong. So here I've actually been able to model TLP based on the leaf densities that I had, as if I weren't able to measure them quickly. The benefit of being able to measure them quickly is that I can actually test this against real data. So here we have my modeled TLP and my actual measured TLP, and it's a pretty strong prediction. Again, this is a trait that's pretty easy to measure, but it's totally showing the validity of this approach because it works. Cool. That's it for now. The next steps for me are to incorporate the VPD stuff that Peter was kind of talking about. That's actually throughout the system, which will allow me to take what is now an index for time to leaf damage and turn it into an actual time, so I can make a prediction. If we stop watering the plant, this is what will happen. There's a lot of complexity in that beyond that, so it's kind of a simplified version of that, but at least it's a start from the leaf perspective. And then the next thing is to scale that, like I said, with all of that complexity of the whole rest of the plant. We have sap flow measurements for a lot of trees, so that's like our big, super labor-intensive, time-intensive performance trait that I can then try and put all of these functional traits together and predict best that performance trait. And then I can also try and predict the drought tolerance when I get my TLD stuff together, and something with stored water in the stem and the roots. That's going to be a whole other beast, but you got to dream big. And yeah, and so then the big dream is to scale all of that to the landscape level, because we have all these amazing surveys from people in this room, I'm sure, done this amazing work to do all these surveys. And I would love for that to contribute to more sustainable LA and future xeriscaping. So with that, thank you. I'd like to thank you guys for having me and my advisor and all of my lab mates who, everything we do is collaborative, so.